Lesson 30 has two parts. The first part is on Pascal's Triangle and the binomial theorem. And since Lesson 26, we've been working with polynomials higher than degree 2, but mostly just degree 3. And that's normally what you do in Precalculus. There's not a lot higher than that. But anyways, here we're going to introduce some simple ways to quickly expand binomials of any degree using an amazing pattern known as Pascal's Triangle. And we'll also look at a formula called the binomial theorem, which basically does what the Pascal's Triangle does in formula form. So when you do the practice sets, you can apply either one of these to the problem. So you can use Pascal's Triangle to find the term that you need, or you could use the binomial theorem, whichever one you want. But this is something to make a note of. As a general rule, binomials of about degree 6 or less use Pascal's Triangle, and then binomial theorem for anything larger. So a little history on Pascal's Triangle. It's named after Blaise Pascal, and he was one of René Descartes' contemporary critics. And we talked about René Descartes before. Pascal, he noted, as we have, that Descartes' idea of "I think, therefore I am," that's a nonsense idea. And he said that that resulted in the expulsion of God from the world because it just had this focus on self instead of the connection to God. We exist because God created us, not because we're able to think or not think. But even Pascal's idea isn't that great because God can't be expelled from his own creation. So what Pascal was saying was that Descartes' idea resulted in a fake worldview in the minds of some people who followed and supported Descartes' belief. So a good book that talks about Pascal, Descartes, and other people and how their beliefs and thoughts about God influenced mathematics, that's found in a book called Mathematics Is God Silent by James Nichol. So a good history of mathematics book you might be interested in reading there. But anyway, Pascal, he developed his triangle around 1644, and it has many uses, but here what we're going to use it for is to expand binomials, and that is a use discovered by basically the greatest scientist in history, Isaac Newton. And let's just do Pascal's Triangle. That's the best way to get familiar with it. It's very simple, and just be thinking, I mean, it's a triangle made out of numbers is really what it is. So you start with 1, and then you put, next row, 1s on each side. Next row, you always start and end with a 1. And the middle term here, this row is going to have 3 terms in it, so the middle one's going to be the sum of the 2 right above it. 1 plus 1 is 2. And then the last term over here. Then the next row, start and end with 1, and we add, so here plus here, 1 plus 2 is 3. That's the next term. And then 2 plus 1 is also 3. End with a 1. Next row, start with 1. Look above. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 on the end. Next row, 1 right there. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And end is 1. What are we doing? We see this pattern that we're creating here, and it's very easy. You don't have to memorize the whole triangle that we just had there. You just start with a 1, then you go 1, 1, then the next row, start and end with 1 the rest of the time, and then you add the terms in between the 1s are the sum of the 2 right above them. So maybe try to fill out the next row that we have there for the Pascal's Triangle. So it'd be a 1 here, a 6, a 15, a 20, because 10 plus 10 is 20, another 15, a 6, and a 1 on the end. Now, here's a little nicer, neater Pascal's Triangle in the middle there, and you can see the binomial that goes with it. And this is what we're using Pascal's Triangle for, is to figure out what the coefficients of an expanded binomial equal. So, starting with a binomial of x plus y, or f for first, s for second term, f plus s to the 0 power. Anything raised to the power of 0 equals 1, right? So the coefficient is 1, the expanded binomial is just 1 for that. Then the next row, f plus s to the first power. We have that would just be an f plus s, right? Then f plus s to the second power, we have a 1, 2, 1. So these terms are coefficients. 1, 2, 1. 1 f squared 2 fs 1 right there for the s squared. It's understood those ones are there in the algebraic expression, so we don't write those. So 1, 2, 1. Then you see the 1, 3, 3, 1 in f plus s cubed. So we get 1 f cubed plus 3 f squared s plus 3 fs squared plus s cubed. Then next row is f plus s to the fourth, and so on. And you can just see how those coefficients that you create in the Pascal's triangle, where those go, and it's just in order as you move left to right through an expanded binomial. Notice the exponents in the binomial as well. So for example, if it's f plus s cubed, when we expand that binomial out, it's f cubed first, so it's like f cubed s to the 0, and then we drop down 1 on f cubed down to f to the second power, and then it's s to the first power. Then we drop down again on f just to plain f to the 1 power, and then up 1 on s. So we go down 1 on the first term, up 1 on the second, and you just move left to right like that. So there's lots of patterns that come with expanding binomials. That's some of the interesting things about them, and it makes it not as difficult. If you see those patterns, you don't have to feel like you have to memorize everything. Just recognize those patterns that are going on. That helps you with expanding them the right way. It helps you figure out what coefficients to use in which places. Well, the best way to learn Pascal's triangle is to do some problems. So let's do some problems. Example 30.1. Create a Pascal's triangle for f plus s to the 7th. Then answer the following. Now we did say as a general rule you use it to f plus s to the 6th, but let's just do it to the 7th here just for practice. So just go ahead and create that Pascal's triangle. Try to do this on your own, pausing the lesson. And so you'd start with 1, then 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, 1, 7. Here's our 7th row there, f plus s to the 7th, 21, 35, 35 again, 21, 7, 1. So we want to do A, expand x plus y to the 6th. So for that, we just need to look at this row here, and we can tell that that's the f plus s to the 6th row. One way you can tell is just by that second term that you get there, that second coefficient. It's a 6, and that's a hint that that's the f plus s to the 6th row. So if you recognize things like that, that keeps you from having to go, oh, well, this is the f plus s to the 0 row, then it's the f plus s to the 1 row, and so on. You can skip having to do all of that. So A, expand that out, we'll just say x to the 6th plus 6. And see, now this is where we go down 1 with the x exponent, and then up 1 with the y. So it's y to the 1 now, or just y there. And then plus 15, x, we go down 1, so that'd be a 4, up 1 with the y squared. And then plus 20, x cubed, y cubed, plus 15, I'm just going to move down here, 15, x squared, y to the 4th, plus 6x, y to the 5th, plus y to the 6th. And that's it. That's the expanded form there. In B, find the third term of x plus 2y to the 5th. So what we can do is use Pascal's triangle to find the coefficient. So the third term of that 5th power row, that'd be right here, what I just circled there, the 10. So that's the coefficient. And let's think about the third term there. Well, the first term, what would that be? That would be x to the 5th. Then we go down, x to the 4th for the second, x to the 3rd for that third term, and then it would be parentheses, this is very important here, parentheses 2y to the second power. So we need to do 2y times 2y, that'd be 4y squared. So we get 10x cubed times 4y squared is equal to 40x cubed y squared, like that. And so that would be that third term. And then in C, the fourth term of x squared plus 3y to the seventh. So look at that row with the 7, that has the 7 as that second coefficient there. Looking at the fourth term, that would be a 35 in that row. So another way to write these to start with is say 35, and then what's our first and second coefficients here? We're looking at the fourth term, so we'd start with f to the 7th, 6, 5, 4. So it's like f to the 4th, second to the third power. And then we'll substitute in 35. The first term is x squared, so we'd say x squared to the fourth power. And then the second term is 3y, so that's to the third power. And so then we'd end up with 35x to the 8th, and then 3y cubed, that's 3y times 3y times 3y, that's 27y cubed. So be careful on those, don't just say 3y cubed, it's 3 times 3 times 3. So 35x to the 8th, 27y cubed is 945x to the 8y cubed. Let's move on to example 2, and here we'll use the binomial theorem, and that's mostly used for answering questions like the one we just did, example 30.1b and c, where there's a specific term you want to identify. That's what that binomial theorem is for. And formulas like this are often referred to as plug and chug types of formulas, where you just plug in your numbers and you chug away like a train as you do your calculation. So let's do a few plug and chug problems where we use the binomial theorem. So in A, the fourth term of x squared plus 3y to the 7th, well, that's the same problem we did in C, 30.1c, but we'll just use the binomial theorem, and we should end up with 945x to the 8th y cubed again with that. But let's just write that formula down first. N factorial over n minus k plus 1 factorial, parentheses k minus 1 factorial, and then times f. So look at this exponent. It's the same as the what's in the parentheses on the left down there. N minus k plus 1, and then s to the k minus 1. So you don't have to keep remembering the same thing over and over again. So for A, we want to do the fourth term of that x squared plus 3y to the 7th. So n, that's our power of the binomial, 7. So we do 7 factorial over 7 minus k. K is which term we want, the kth term, so it's the fourth term. So we'd say 7 minus 4 plus 1 factorial times 4 minus 1 factorial times f. We'll just say f right now, we won't substitute the variable in yet. But that's going to be to the exponent of 7 minus 4 plus 1. 7 minus 4 is 3 plus 1 is a 4. And then s to the 4 minus 1, s cubed. So then let's just keep simplifying here. We'll end up with 7 factorial over 4 factorial times 3 factorial. And then our f term is x squared. So that would be x squared parentheses to the fourth power, and then our s term is a 3y, so 3y parentheses cubed. So there's different ways that you can deal with all of these factorials. You can break them down and say like 7 times 6 times 5 times 4 factorial over 4 factorial times 3 factorial, which actually that's just 6, right? It's 3 times 2 times 1 is 6, and you can see the 6's would cancel, the 4 factorials would cancel, you're left with 7 times 5 is 35 over 1 is 35. So you can do it that way if you want to, but sometimes if there are a lot bigger numbers than that, then just go ahead and get your calculator out and use your factorial button on your calculator. So here we'd get that 35 and then times x squared to the 4th power, that's x to the 8th. And then 3y cubed, that's that 3y times 3y times 3y is 27y cubed. And so then we do 35 times 27, and that is 945 x to the 8th y cubed. So we've actually shown here in example 30.1 and 30.2 two ways to get that 4th term, one using Pascal's triangle, one using the binomial theorem. Moving on to B, we want to find the 5th term of x minus y to the 10th. So find that 5th term relative to fs, the first and second, just like we just did in A, and then substitute variables in. So applying the binomial theorem again, we'd have 10 terms in this binomial, so that's 10 factorial over 10. Want the 5th term, so that's minus 5 plus 1, parentheses, and then factorial on the outside of that, and then 5 minus 1 there, k minus 1 factorial. And then this would be the first term to the 10 minus 5 is 5 plus 1, that's a 6. And then second term to the 5 minus 1, that's a 4 to the 4th power. So 10 factorial over 6 factorial times 4 factorial. And then the first term, f, is just x. So it's x to the 6th. The second term is a minus y. So that's important on that. That's minus y to the 4th. Because there's a minus right here, we need to think of that as x plus a minus y. So that minus has to go with the y. And if you had a cubed problem, that would be an even more important thing, or to the 5th, like an odd exponent, because you're going to end up, when you simplify that, you'll end up with an odd result. But here it's just minus y to the 4th. That would give us an even, a positive y for a result. So you could do 10 factorial over 6 factorial times 4 factorial on your calculator, or you can expand those out and cancel like the 6 factorials and things like that if you want to. You should get 210 x to the 6th, y to the 4th. And that's the 5th term of x minus y to the 10th power. Let's move on to part B in a different concept, distinguishable permutations. And let's think about the fundamental counting principle and related ideas like permutations. Those allow us to consider things like order and choice making. And if you want to find the number of permutations or ways to arrange the letters in the word Alaska, for example, one thing you might notice right away there is you've done arrange the letters in a word problems before, but this one, the A, is repeated, right? There's 3 of them in Alaska. So how do you distinguish one A from another one when you do the permutation? Well, one way you could do that is you could use subscripts. So A subscript 1, A subscript 2, A subscript 3. So you might have this as one permutation, one arrangement of the letters. Another arrangement might be that. But normally that's not how we write letters, right? We don't put subscripts on letters. So to really find out the number of distinguishable permutations, the ones that are truly different from each other, we need to cancel out 3 factorial. So that's not an emotional 3 there saying we need to cancel out 3. No, we need to cancel out 3 factorial is what we're talking about there. So, I mean, you can be emotional about it if you want to, but that's not the point. We cancel out 3 factorial since that removes the effects of order from the repeated A's. So that's why we're doing that. If we had the word aardvark with one letter repeated 3 times, see how that A is in there 3 times, but then the R is in there just 2 times. Then we need to factor out 3 factorial for the a's, 2 factorial for the r's. In other words, we need to divide through by that, the total number of letters there. So there's no specific formula for distinguishable permutations because they're kind of unique to each problem. You just need to find which letter or letters repeat, divide by the corresponding factorials. As with most math, it's best learned by doing, so let's do some examples here. And let's start with Alaska. 30.3a, what's the number of distinguishable permutations in the letters of the word Alaska? So, well, how many letters do we have there? We have 6, right? 6 letters in the word Alaska, so we just have 6 factorial. That's like the total number of ways right there, and then divided by 3 factorial, because the a repeats 3 times. And so we get 6 times 5 times 4 times 3 factorial over 3 factorial. Those cancel and we're left with 6 times 5 is 30 times 4 is 120. That would be the number of distinguishable permutations in the letters of the word Alaska. In B, aardvark, the number of distinguishable permutations, ones that are really different from each other. So in other words, we're not labeling those a subscript 1, a subscript 2, r subscript 1, and so on. We just see that there's 8 letters, so the numerator is the number of letters, 8 factorial. And then over 3 factorial to remove the effects of the a being repeated, and then 2 factorial to remove the effects of the r being repeated. So you can do this on your calculator, or you can expand it out. However you want to do that, you should get 3,360. So do that. Don't just take my word for that's 3,360. Remember, you're supposed to do the calculations here. That's how you learn how to do math, is by doing it yourself. C, 12 marbles. If 6 are red, 4 are blue, 3 are yellow, the number of distinguishable permutations there. So we always put the total number of things in the numerator when we're doing distinguishable permutation. 12 total things there. Over 6 red, 4 blue, 3 yellow. So that means 6 factorial times 4 factorial times 3 factorial. So get that calculator out, whatever kind it is. It doesn't matter. Like this one on a Macintosh Apple computer, can clear it out there, and you can say 12 factorial divided by 6 factorial. That equals that right there. And then divide that by 4 factorial. And then you can divide it by 3 factorial, or just know that 3 factorial is 6. 4,620 would be the result. And that is all you have to do. So obviously a key word on problems like this is distinguishable. We're not just finding the number of permutations, number of ways we can arrange them, but the number of distinguishable permutations. And when it's from lesson 30, that's also an indicator to you that this will have something that repeats itself, and you factor that repetition out with a factorial. And that is all for lesson 30.